input to our predictor is the sum of desired sequence plus noise. Okay? The past class, the desired sequence was exactly equal to the input. Now we have this difference. The desired sequence is not equal to the input. There is some noise that often is called measurement noise. Measurement noise that is additive and it adds to the desired sequence in this way. Then we make prediction. Here we have prediction, and this will be the error. So S is equal to D plus N. N is white noise, independent of the desired sequence. Good now. Note that in the practice we always have N, because any measurement, S is the result of the measurement. So any measurement is always, in some sense, affected by noise. What we are saying, the model that we have for this node, the noise is that the spectrum of N is white. Okay? So, try to figure out which is the result of prediction. Well, it is exactly the same as if the desired sequence were S. Why? Because N is Y, so it is unpredictable. So, D maybe is predictable. If it is non-white, then it is predictable. Then I add an unpredictable term. And then I ask to make prediction. Prediction is the same that we would have also if we try to predict S. And this can be seen in this way. CSD of Z, well, it is equal to CS. The cross correlation between S and D, between S and D, if we take the wind ring between minus L and minus 1, they differ only in the power. They differ only in the power. But for K that goes from 1 to infinity, the depths of CSD are the same as the depths of CS. So when we have the usual winner of equation, CS by H equal to CSD in the case of prediction of S, this S is the desired sequence, so this is the vector of CS from 1 to infinity. In the general case, we put in place of CS, CSD. But when D and S are related in this way, then CSD is equal to CS. Okay? Remember that this vector in prediction starts from CSD1 and then goes on to CSD2, CSD3, blah, blah, blah. Huh? Okay, so the optimum filter is exactly the same that we found Friday, and that comes from the spectral factorization. What changes is the mean square error, because in the conventional prediction so hat D is the same. Call this one, I don't know, E prime. This is the error that we make when try to predict S. This is the error that we make when we try to predict D. Okay? Because H is the same in the two cases due to this equality. But the only difference is that this contains also the noise from this part. While this D does not contain the noise. That is, the noise comes only from this part. This is the only difference. So what we must expect is simply, since we have changed the definition of the D of Z, we must change accordingly the error. Nothing else than this, okay? So now this error here this is also hat S of Z, it is the same, the two are equal. So S minus hat S will be equal to D plus N minus hat D. This is because S is equal to D plus N. So this is what we are calling E prime, and this is E plus N. Okay? Good morning. Is it clear? Can I proceed? Can I go on? Questions? The expectation of S minus at S to the square will be equal to the expectation of D minus at D plus N to the square, and by independency between N and the rest, we have that this is the expectation of D minus hat D plus the expectation of N to the square. So in the end, we have that D minus hat D, which is the error that we are looking for, is equal to alpha to the minus 2 minus the expected value of the additive noise. So look to this passage, this equality here. This means that n is independent of d, and since n is unpredictable, there is no trace of n into hat d. Okay? It is unpredictable, so prediction is independent of the unpredictable part. This is the reason why here we have the sign. So if we look to this formula in this way, what we are saying is that the error between the input and the prediction is equal to the error between the desired sequence and the prediction plus the unpredictable noise. Plus the power of the unpredictable noise. Okay? Questions? Okay, this is the case. Make an example. We can consider again the sinusoid with random phase plus additive noise. Okay, we linearize the model, and after linearization, we have that the input sequence is the theta plus the noise. Okay? This is after linearization. And then consider, for instance, the feedback. The feedback loop. The feedback loop, that is prediction in feedback form. Okay? Error is S minus F theta, and the CS is gamma to the square 1 minus Z, 1 minus Z to the minus 1 plus the noise times the signal to noise ratio. But if we perform the spectral factorization of this spectrum, we find the whitening filter and the predictor. The predictor takes the form 1 minus Zp, Z to the minus 1 divided by 1 minus Zp z to the minus 1, where Zp is exactly equal to the pole that we found with the two-sided filter. It is, let us record it, 1 plus gamma to the square the signal to noise ratio minus the square root of 1 plus gamma to the square signal to noise ratio everything to the square minus 1. This is the pole, and the alpha is 1 divided by 2 times SNR ZP. This is H. If we put it in feedback form, we need G, which is H divided by 1 minus H. 1 minus Zp z to the minus 1 divided by 1 minus z to the minus 1. From this alpha we can compute also the expectation of theta minus hat theta. That is, basically I'm using the same equations as with prediction of S, at least the same equations for prediction of S for the filter, because as we said, prediction is the same in both cases, but if we want to predict this and this, so the filter is the same. The G is the feedback form. Alpha to the minus 2 comes from the spectral factorization. Remember, 1 minus H alpha to the square 1 minus H star to Z to the minus star equal to 1 divided by CS. This is the factorization that we must perform to find the optimum filter H. Then from H, which is in flow form, we can implement the filter in feedback form, like that. And from this alpha to the square, we find the mean square error between theta and hat theta, which is the same as the mean square error between S and hat S, excepting the noise. Here is the noise term. Now if we substitute in place of alpha this equation with this Zp here, we can proceed and find the formula that is this one. Now let Zp go to 1, that is narrowband filter, that is high sampling frequency compared to the bandwidth of the filter, which can always be obtained. this case, we approximate this as 1 minus ZP divided by 2 times the signal to noise ratio, which in turn can be approximated as the square root of gamma to the square divided 2 times the signal to noise ratio. So very simple formula. And it is also very intuitive, because this means that the mean square error is proportional to gamma. Of course, the greater is the step size in the random walk, the more difficult is to track the random walk and to estimate it. And this is the inverse of the signal to noise ratio. So the noise is at the numerator and the signal is at the denominator. So the action of the noise is that of making difficult the estimate of theta, that is extracting theta from the noise. Okay? So remember, this spectrum is related to this process. Where U is Gaussian noise. So if gamma is big, and I know only the past, of course the error, the theta will be far from theta k minus 1, and will be difficult to predict theta, having access only to the past. And this is the reason of the gamma to the square at the numerator of that square root. Moreover, besides this process, there is also the noise, you see? And the noise makes prediction of theta difficult, because the measurements are affected by noise. And when you see a noise in measurement, it can be difficult to see what is embedded in noise. And this is the reason for this SNR at the denominator. Okay? Also note that this is a square and this is a square as well. And everything is below the square root. Questions? The ZP is exactly the same that we found for the two-sided filter. Okay, so if we go back to that class, here we have the frequency in the log frequency. Here we have the log of CS in the frequency. Well, actually this is psi theta, this is the psi of the noise. The frequency where they meet is exactly equal to the corner frequency of the filter, so the difference between the non-causal and the causal filter is simply in the slope. With the two-sided filter, the non-causal filter, we have a frequency response like this, which is approximated by this Bode diagram. And here, at the corner frequency, the attenuation is 6 decibels. And then the slope is minus 40 dB per decade. With the causal filter, we have a pretty much similar frequency response, but we have only one pole, you see? Only one at the ZP. So here the attenuation is minus 3 decibels, and then the slope is a first order slope that is minus 20. minus 20 dB per decade. Remember that this filter has a frequency response which basically is the square of this one. This is what we call HC, the causal. You see, this is causal, one causal. And we called this HC in the class on the two-sided field. If we look to the impulse response of that filter in time, it starts from 1 and goes to infinity, and basically it is obtained by sampling, the decaying, one-sided decaying exponential. Okay? This is the usual first order integrator with leakage that you studied in the first lab of DC1. The usual one. The normalized bandwidth of the filter is bandwidth. So this is noise bandwidth depends on the pole. So as usual, you can divide the mean square error into two parts. The first one obtained due to the noise, the additive noise. The second one due to the phase, which is not tracked. You remember we can split the mean square error into two terms. If you look to this picture, you see that what is inside the estimate? The filtered version of wanted plus noise. Okay? So, due to filtering in the high frequency region, there is a distortion of the high frequency components of the theta. So, forget about the noise. Forget about the noise and look to what you want and what you get. What you get is a filtered version of what you want. So due to filtering, what you get is not exactly what you want. There is a difference, which is this one. Now forget about theta and look to the noise. Of course, in the estimate there will be some noise. And the power of this noise is exactly the power of the white noise filtered through the H of Z. Okay? So, this is the reason of this type. This term here is the noise bandwidth multiplied by the noise power. And after some passages, we write the second term in this form. So, as Zp goes to 1, this goes to Bnt divided SNR plus Bnt divided by SNR. So So the two terms become equal one to the other for narrowband filtering. Narrowband compared to the sampling frequency. This is the integral of the noise after the filter. So noise banded by the power on the half band. And this is the integral of the high frequency components of theta that are not recovered in the estimate due to the filtering. So this is the frequency response, this is the noise. What at the output? Well, at the output we will have exactly this multiplied by the power spectral density of the noise here. And this area is the noise in the estimate, which is this one. That is exactly this. Okay? This is one source of difference between what you want and what you get, the noise. The other source of difference is the phase. That is, you want this, and what you get is the filtered version, which is pretty much similar to the -20 till the -3 decibel point. And then you must multiply these two, it is -40. But what you want is this. And so here there is a difference between the two spectra. This is what you want. And this is what you get. I mean the spectrum of what you want, that is the spectrum of theta, and the spectrum of what you get in terms of phase, which is the true theta multiplied by the squared modulus of the frequency response of the filter. So at low frequency, the theta that you get is pretty much similar to the theta that you want, because here the frequency response of the filter is flat. So the low frequency components of theta are well recovered after the filter. The problem is with the high frequency components of theta, because here you find the slope region where the filter attenuates, and so the high frequency components of theta are attenuated by the filter. And at the output of the filter you find a slope that is -20 and then -40, while the true slope of theta is -20 everywhere. The difference between these two spectra is this term. Okay, so this term is this difference, while this other term is the spectrum of the noise after the filter. It's exactly the same trade-off that we already discussed with the two-sided filter. And again, if you look to put here the noise bandwidth of the filter, and here the estimation error. It will be like this, and this is the optimum noise bandwidth, that is the one obtained by with this ZP. Where is it? Well, with the optimum ZP. For narrowband, this term becomes dominant, because with narrowband the difference starts from low frequency. If you use a filter with narrowband, what happens? That the error has a spectrum like this, the error on theta. This will be lower because the noise bandwidth is reduced, but this term increases. And on the opposite, in this region, the wideband of the filter becomes like this. The spectrum of the error on theta becomes like this. So the difference is lower, but there is much more noise because you are using a wideband filter. So the usual compromise. You want wideband to recover the high frequency components of theta, but at the same time you want narrowband to reject the noise. At the optimum, the power of the error is equally divided between the first and the second term. So basically, this is the expectation with respect to theta, and this is the expectation with respect to the noise. And what you make is the sum between them. And the optimum is obtained when the two are more or less one equal to the other. If we compare this formula to the mean square error that we have with the two-sided filter, we find that this is worse of 3 decibels. The mean square error on the phase with a one-sided filter is 3 decibels higher than the mean square error with the two-sided filter. This is quite intuitive. We are renouncing to half of the knowledge about the phase. In the two-sided case, we can observe the past and the future and make an estimate now. Okay? With the one-sided filter, only the observation of the past is possible. So half of the samples. Half of the sample, 2 times the squared error. Formula for the mean square error of the theta. It goes, this is one-sided, and they call that is approximated to 8 times the signal to noise ratio for the two-sided filter. Two-sided, one-sided, I'm referring to the impulse response. Okay? That is two-sided is non-causal. one-sided is the causa. So the two impulse responses are this one for the one-sided and something that we call this for the two-sided. This is time. Time H. Well, one-sided means causa and two-sided means non-causa. You can use this one when you can wait, because in the practice, in the very practice, all the filters are really causal, so in the end, this is the real shape of the impulse response in the implementation, of the two-sided impulse response implementation, meaning that you must accept a delay in the estimate. So if you can wait, you can improve the estimate of 3 decibels compared to the case where you cannot wait. You cannot wait for the estimate. Of course, in prediction, you cannot wait. You have the past information. You cannot wait for the future before making prediction. You must perform prediction before the new sample arrives. Okay? So this is the case of prediction. Yes?
When we say that the one-sided error is more,
Yes.
we see the expression that is less.
No, the two-sided is 8 at the denominator, which is 1 over 2, the 1 over 2, the square root of. And this is the one-sided. This is the one-sided. So the two-sided is half the one-sided. But this is intuitive. You have access to more information. You can see the past and the future. The only difficulty is that the sequence that you want is in noise. Is embedded into additive noise. This is the only difficulty. With the predictor, you have one more difficulty. You don't know the future. You only know the past. So you have access to half of the samples, which are of course embedded in noise again. Questions? So, this concludes the part of MMSE. Now, let's look to the first application, that is PLL, phase lock loop, with application to carrier recovery and timing recovery. That is synchronization of digital communication receivers. The PLL, phase lock loop, is say subsystem, a circuit that is widely used in electronics and in telecommunications. Inside your smartphone, there will be, I don't know, at least 20 PLLs. Okay? There are two versions, as usual, of the circuit. One is in the continuous time domain, the other one is in the discrete time domain. We will start from the discrete time, using therefore the discrete time sequences and the Z transform when we will linearize it. Basically, we have an input, a nonlinear function, a detector, which is a phase detector, a loop filter, was transfer function, I will call it L as loop, L of Z. Here you have the phase error, and here you have the control signal to another subsystem that is called NCO, number controlled oscillator, and we call this B. This is number controlled oscillator. The idea is that I want to control this oscillator in such a way that it produces a signal whose phase is close to the phase of the input. That is, I want that the phase of Y and the phase of V are close one to the other. To do this, basically, intuitively, to do this, I measure the phase error and I filter it and try to reduce the error by controlling the phase of V through the number controlled oscillator. So if this phase is greater than this one, then please increase. And this is seen by looking to the filtered version of the error. And on the opposite, if the phase of this one is lower than, this error drives the loop to a lower value of the phase. It is the classical feedback system. Very classical feedback system. Okay? Now, let us characterize the tree. Well, for this, no problem. It is a filter. So it is completely characterized by its transfer function L. Okay? Let us see what is the number controlled oscillator. The output is an exponential, a complex exponential of a phase Ck, which is controlled in this way. So, according to the control, increase or decrease the previous value of the phase. Basically, the block diagram is, this is C, add, find the C, is Z to the minus 1, and here take the complex exponential of the C to get the output V. This is the block diagram of the number controlled oscillator. So this is zero causal, and to make the loop causal, we require that the L of Z is one causal. It will have a form of the type the sum for k that goes from 1 to infinity of Lk Z to the minus k. One causal and stable. You must impose a stability, of course. Well, no. Stable will be the loop will be stable. We don't need to require stability of L. What we want is stability of the closure loop, which is a slightly different concept. Okay? What happens if C is a constant? What happens to psi? Suppose that Ck is a constant. That is, this is K, this is Ck, and Ck is constant, like this. What happens to psi? Psi is a ramp. It increases. Don't care of the infinity that it reaches, because it is a phase. So you can reduce it modulo 2 pi. Yeah, you can put the sum modulo 2 pi, because in the end what you need is a complex sinusoid with this phase. So this sum can be modulo 2 pi. So if C is constant, C is a ramp, meaning that here you will have for V, real part of V, imaginary part of V. In time, look in time what happens. Yes, exactly. You will have an increasing phase like this. K equal to 1, K equal to 2, K equal to 3, K equal to 4, and the phase difference is C. Okay? This is for positive input. It rotates in this way, clockwise, decreasing. This is for negative input, sorry. C lower than 0. Decreasing phase, clockwise rotation, while for positive input, like this, real part of V, imaginary part of V, for positive input, this is C, this angle, and this will be K equal to 1, K equal to 2, K equal to 3, K equal to 4. So basically the output is a complex sinusoid whose frequency is proportional to the control signal. And you see here the phase actually is the integral, this is the integral of the frequency. Frequency is the derivative of the phase. You can write Ck as Ck minus 1 plus Ck, that is Ck minus 2 plus Ck minus 1 plus Ck, dot equal to the sum for k that goes from minus infinity, for I that goes from minus infinity to k of Ci. It is the integral. phase frequency. And what about a non-constant CK? Well, the non-constant CK will be the instantaneous frequency of the complex sinusoid. And here you will have a frequency modulation, where the modulating signal is CK. Now let's look to the phase detector. Basically, the PLL is a circuit that assumes that the input is a sinusoid. In this case, a complex sinusoid, because we are looking to the baseband equivalent. In this case, the output is a signal that is a function of theta minus c. So the phase detector is a nonlinear transformation with two inputs and one output. The two inputs are two complex sinusoids, one from the environment, the other from the loop. And the function of the phase detector is to extract something that is a function of the phase difference, meaning that I don't care of the amplitude. I don't care of the amplitude. So it can be something like this. R. Okay. Of course, since the error is a function of a phase difference, it must be periodic. It must be periodic, because you will never recognize phases with the multiplicity of 2 pi. Multiplicity of 2 pi is always dropped when you measure the phase. And here you are measuring a phase difference. So you will have a measure which is ambiguous. Okay? The specific F is a characteristic of the specific phase detector. Ideally, we would like to have an F like this. Pi, 2 pi, 0. This is the ideal phase detector. It gives you an error which is exactly proportional to the phase difference modulo 2 pi. So here you will have minus pi and minus 2 pi and so on. Okay? How can you build a phase detector? Well, For the NCO, no problem. This is accumulation, and this is a lookup table, a read-only memory. So basically, this is a filter. The only difference with the filter is that here the sum is modulo 2 pi. Okay? And this is a read-only memory, or a lookup table, call it as you want. Meaning that this is the address of the memory, and this is the content of the memory corresponding to that address. So a table where this is the entry of the table and this is the output. A map and the field. What this is the usual filter. You can make it as typically you will make this as an IIR filter, feedback filter. Anyway, it's the filter. What about this? Well, for instance, you can obtain this by making the argument of y by v star. That is, take the complex conjugate of v, it will have a phase that is minus psi, multiply, you get a complex exponential that has a phase that is theta minus psi, and then extract the phase. This is an example of phase detector. Okay? You see? If here there is an amplitude, it disappears because you extract the argument. If here there is amplitude noise, it disappears. Only the noise that goes on the phase will affect phase detection, not the amplitude part. Okay? Well, this is a feedback loop, which is the steady state of the loop. The steady state is when the error is a zero. When the error becomes a zero, there will be no more action. The loop filter will discharge, and the C at a given point will become zero. When the C is a zero, the phase is constant, and the error remains equal to zero if theta is static, is a constant. Suppose that theta is a constant. At the beginning, the NCO is initialized with a phase that depends on the content of this memory. You don't know theta, so you put here what you want, for instance, a zero. And here there is a zero phase, here there is a phase that is theta. The error is theta, theta goes into the loop, and here you will get that the zero moves smoothly because of the filter, smoothly towards the theta. When this phase is equal to this phase, the error is zero, and after the discharge of the loop filter, the C is a zero. At this point, there is theta inside this memory, theta here, C zero, and here you have the exponential of, the complex exponential of theta. And the loop is okay. I have reproduced here the phase that is contained here. Now suppose that the phase here moves, makes a jump. Well, again, there is a transient such that the loop smoothly recovers the jump. Okay? This is basically the working principle of this feedback circuit. So, the condition of a small error, well, some noise will always affect this input, so the error will be never exactly equal to 0. First of all, because theta will be a function of time. So it will move, and through the loop, the circuit will track the movements of this theta. And second, because there will always be some additive noise contained into the measurement. Okay? So the error will be never 0, but it can be small. And when it is small, we say that you are at phase lock. That the phase lock is exceeded. So the phase lock condition is small error. If the error is small, when theta moves, the error becomes a little bit greater, and thanks to the action of the loop, the feedback system reduces it. Okay? So tracking the time variations of theta. Of course, we also want this. The mean value of the error is 0. So sometimes the estimation here is with positive error, and some other times with negative errors. So the phase lock condition is made by these two. This means small variance of the error, basically. Small variance, and this means 0 mean value. Note that there can be an offset between this node in the function of the phase detector and the 0. Nothing changes. That is, if I have a phase detector like this, the error is 0 when theta is equal to psi. Okay. Now suppose that I have a phase detector like this. The error will be 0 when psi has an offset compared to theta. But the phase detector is a deterministic function, so we know this offset and we can recover it. Basically, we can say that hat theta is equal to psi minus psi plus 2 pi times. So now what is this? Psi is this angle here. So psi is the crossing point, this psi here. And this will be psi plus 2 pi, psi plus 4 pi, and blah blah blah. The estimate is proportional to the psi k, the angle here, with the offset. So bring back everything of this offset. And so the phase lock condition means theta minus hat theta small. This is phase lock. Questions?
phase lock, the estimation is finished.
Is,
And there is nothing more to estimate.
yes, the point is that in the reality, this will be time varying. So ideally, if this is fixed, not time varying, yes, you can exactly recover theta by the loop. And the error is zero, and then at that point you are at the steady state and nothing moves. But in the reality, theta will be a function of time. For instance, random phase walk. And also, you will have additive noise, like this, plus n, which is another source of time variation of the phase of y. So in the reality here, things continue changing, and this change must be tracked by the loop, and so also V will change. And there will be an error, exactly as we have seen for the theory of the mean square error. You try to estimate theta, but due to its time varying nature and due to the noise here, there will be something that is not exactly theta, it is hat theta. And there will be an error between theta and hat theta. When this error is small enough, we say that the system is in the tracking condition at the phase lock. This is because not all the phase detectors, as we will see, has a form like this. There are certain phase detectors, as the phase detector of decision-directed carrier recovery, where the error, here you have theta minus hat theta, and here you have the error, where the error has a shape like this, and then you have the 2 pi. This is a phase detector, because generally speaking, the phase detector is simply a function of the phase difference. This writing means don't care of the amplitude. The only variable of this function is the phase difference. But how is this function? Well, it can be as you want, depending on the system and on the design of the phase detector. The ideal case is this one. But not always it is possible to have a phase detector like this, as we will see. For instance, we will see in carrier recovery that the actual shape of this function is something like this. So, in this region, you have a good phase detection. The output of the phase detector is proportional to the difference between the input phase and the estimate. But in this region, the phase detector basically does not give you a good information about the phase difference. Okay, so when the error is small, you are at the phase lock, and you can try to track the input theta in time. When the error is large, it is out of lock. Okay? Because the output of the phase detector has nothing to see with the... Yes, it is a function only of the phase difference, but it is not proportional to. Really, what we would like to have is a phase detector that is always proportional to the phase difference. But as we will see, not always this is possible. Not always. It depends on the specific system. Actually, when y is a sinusoid, you can perform phase detection in this way. And this will be ideal. but sometimes it happens that y is not exactly this one. Anyway, we will see this later on. Now, let us consider the linear zone of the phase detector. That is, let us linearize this f around the phase lock for small error. For small error, whatever is the shape of this f, it is periodic. And sooner or later, it will cross the axis. You see, with positive slope. This is the zero error, this is the zero error with positive slope. Let us linearize it in these points. That is, for small error, let us write the error as proportional to the phase difference. Okay? Linearization. That is, look to the crossing points and take the slope at the crossing point. The slope is Kp, and this is the difference. Theta minus hat theta. And this will be the f of theta minus hat theta. This is called the gain of the phase detector.